Hello everyone, today in this video we'll be discussing the first module of 21PHY12 and in this module we have the oscillation and waves. So before starting, if you like this video, hit the like button and don't forget to subscribe to my channel. So let's go through the overview of what is there in the module 1. So mainly we have 4 topics. It's about the oscillation and waves. Okay, so oscillation has 3 topics and waves has 1 topic. Okay, so in the oscillations, the first one is the free oscillation, second is the damped oscillation, and third is the forced oscillation. Coming to waves part, we have shock waves. Okay, so in each of these topics we have some derivations and some theoretical concepts which we need to keep in mind before going to exam. So let's get started with the first topic, which is free oscillations. Okay, so in this topic we have mainly derivation of differential equation for SHM, and in mechanical simple harmonic we have 2 derivations, series and parallel combination, and this is just the formula. Okay, so we have 2 derivations, 3 derivations here in the first topic. So let's get started with it and understand how the derivation is derived. Okay, so before starting, let's understand what are the basics of SHM, simple harmonic motion. Okay, so first thing which you need to know is the oscillation. Oscillation is nothing but the repeating motion that occurs when the time varying force acts on the system. Suppose that there is a ball here which is attached to some knob here. So when you pull the ball like this and then leave, it will swing like this, right? That is known as oscillation. Okay, and a few things to keep in mind here. If you don't pull the ball will be at this mean position, right? So if you pull the ball, it will move by a distance x, that is known as displacement. And what is the maximum place it can go? That is nothing but the distance between this and this, right? Because that's the maximum place it can go when it's stretched at the farthest. So that is known as amplitude. Okay, so these are the definitions. Displacement is the distance of the location of the body from its mean position at a particular instant of time. Amplitude is the maximum value of the displacement. Frequency is the number of oscillations per unit time. Angular frequency is the angle covered. Okay, angular frequency means angle covered in the unit time by a body moving in a circular motion. Okay, and this is the formula 2 pi nu. And period is nothing but the time taken by the body to complete one oscillation. Okay, that is nothing but 1 by frequency, which is w by 2 pi. Okay, w is nothing but the angular frequency. Restoring force is the force. See, suppose that if you pull like this ball, you will pull like this, right? At that time when you are pulling it, at that time a force will be pulling it back, right? That gravity force, that is known as the restoring force. When a body is oscillating in a medium, the force acting on the action of a force whose magnitude is proportional to the displacement and acting in a direction opposite to the displacement. Okay, that is known as restoring force. The formula is F is equal to minus kx. K is the force constant and x is the displacement. F is known as the restoring force. This the above equation is called as Hooke's law. So the law states that the restoring force in an oscillating body is directly proportional to the displacement, acting in a direction opposite to the displacement. Directly proportional to the displacement, the more you pull the ball, the more restoring force will be there, and it's acting in a direction opposite to where you are pulling the ball. Okay, that's what the Hooke's law. And what is SHM? The motion of a body is said to be in SHM if the acceleration, which is the restoring force, is directly proportional to the displacement and acts in a direction opposite to the motion of the equilibrium. Okay, so some characteristics of SHM are as follows. It's a particular type of periodic motion. It's a periodic motion. There is a constant restoring force acting on the body. The acceleration developed during the motion is directly proportional to the displacement. Restoring force acts in a direction opposite to the displacement. It is represented by a sine or cosine function, which is nothing but x is the displacement, a is the amplitude, t is the time taken, w is the angular frequency. So x is equal to a sin omega t is the cosine function for the given displacement. Okay, coming to the first derivation, which is the differential equation of a motion of SHM. Suppose that there is a ball like this. Okay, it's of the mass m. Okay, now that ball is attached to a knob here, and you have pulled it like this and left it, so it will move like this, right? Swinging way. So what happens when it moves like this? The displacement is the highest in the amplitude, it comes here, and again when you leave, it will come till here. So it comes to the mean position, which is this. Again it will come back, again it will come here, again it will come here, and so on. Okay, so this is the wave which is forming. In the y-axis is the displacement, and here is the time. Okay, so derivation: consider a ball of mass m and executing SHM. Let x be the displacement of the body under the action of a restoring force. So what is the value of force according to Hooke's law? It is minus kx, right? And what is the means the value of force according to Newton's law? It is ma, mass into acceleration. Acceleration is nothing but the changing in the distance by time. So changing in the distance is dx, and the changing in time is dt. So if dx by dt is v, what is dv by dt? dv by dt is nothing but acceleration, right? So if we write instead of v, we will write dx by dt and differentiate it, it will become d square x by dt square. That is nothing but the acceleration. Okay, so this is the acceleration and this is the mass. F is equal to m into d square x by dt square. Now we will be equating the equation 1 and 2. So what we get is m d square x by dt square is equal to minus kx. Shifting m to the other side, what we get is d square x by dt square is equal to minus k by m into x, and shifting the whole term to the right, what we get is d square x plus k by m is k by m x is equal to 0. Okay. Then we will be replacing one thing. If you observe carefully, k by m is written as omega square. So omega square is nothing but k by m, and so omega will be equal to root of k by m. Okay, omega is nothing but angular frequency. This equation is known as the equation of the motion of SHM. Okay. The solution of the equation 3, which is this equation, if we find out the solution of the differential equation, at that time what we get is x is equal to a sin omega t. If x is equal to a sin omega t, dx by dt is nothing but differentiate this one. So what we will get is omega a cos omega t. Again differentiate, we will get minus omega square a sin omega t. Now this is the same equation which was which we got above, right? This is the same equation which is written here, and then we will be substituting these values which we got here in the equation. Okay. So after substitution, and when we compare 3 and 4, at that time we will get omega square is equal to k by m. See here omega square is there, and here k by m was there, right? So when we compare them, we will get omega square is equal to k by m, therefore omega is equal to root k by m. That was the first derivation, differential equation for a SHM. The next one, the next topic is the mechanical simple harmonic oscillator. Okay, what does this mean is, consider a spring fixed at one end by the rigid support. So let me show you the picture and explain what's happening. Mechanical, so what's the topic? Mechanical simple harmonic oscillator. Okay, mechanic simple harmonic oscillator oscillates in the vertical direction. Okay, now suppose that there's a this is your roof, home's roof, and you attached a spring here, then you attach some mass here, then you pull this mass down and left it. What will happen? The mass will go up and down, like this it will keep on happening, right? So that is known as the mechanical simple harmonic oscillator. Now what we are going to do here is, this is the mean position. If you don't pull, the mass will be at this position. If you pull by x displacement, the mass will come here. Force acting is mg, and this is the limit of the spring. Okay, so this is the diagrammatic representation of from this diagram we are doing two different variations, which is the series combination and the parallel combination of springs. So let's see how those are designed. Okay, so expression, this is the first one, expression for the force constant, spring constant for a series of combination of springs. Series of combination means what? Series means one after the other, one below the other. Okay, so there are how many springs? There are two springs here. The first spring is K1, S1 with the spring constant K1, and second is S2 with the spring constant K2. Now what we are doing, we are adding a mass here. When we add a mass here, at that time the spring will get stretched, and it will get stretched by a distance x1 as well as x2. Why x1 and x2? Let's understand that. Now if you observe here carefully, this is the normal distance where it was initially. When I added mass, it went down by a x1 distance. Okay, this is known as x1. Now that x1 distance, that same x1 distance will also go from the first spring here. This is the first spring, x1 distance, and from the second spring also it will go a little bit down. So that is the x2 distance. So the total distance will be x1 plus x2, and that's what we derived from this diagram. Now let's see how to apply this. Now we will be applying Hooke's law for S1 as well as for S2. So we have Hooke's law, we will be applying for S1 as well as for S2. Then we will do S1 plus S2, so that we will get the total derivation for x. Okay, so for S1 what it will be there, f is equal to minus k1 x1, x1 will be equal to minus f by k1. For S2 similarly it will be minus f by k2. Now we have got for x1 is equal to something, x2 is equal to something. Now what we have written here, x is equal to x1 plus x2. Therefore what we have to write means the total derivation is x is equal to minus f by ks. Minus f by ks means, suppose that the total spring constant of these two springs together is ks, then what is the Hooke's law? F is equal to minus ks, and the total displacement is x in this case, so it will be minus ks x. So what will be x? It will be minus f by ks. Okay, So I've got the values for three of the things. Now by using the equation x is equal to x1 plus x2 and substituting the values of x1, x2 and x, what we get is this one. 1 by ks is equal to 1 by k1 plus 1 by k2. Okay, f will get cancelled from the numerator. Now when we got this one, we will be simplifying it further to find out the value of ks, which is k1 by k1 plus k2 by k1 k2. Okay, so this is the derivation for the series combination. Moving on to the next one, we have the parallel combination of two springs. So two springs are attached here, S1 and S2, by a same mass here. Okay. So applying the Hooke's law, Kp is the string constant for the parallel spring. So this is the generalized form. Fp is equal to total Fp is equal to Kp spring constant for the parallel combination into x. This is the total displacement. Okay. So these two strings are considered as single string, and the displacement which is forming is considered as x, and what is the spring constant of these two together is Kp. Okay. So by using these assumptions, we are writing this formula here. Now we are considering for the each of the individual ones. So for S1 it will be F1 is equal to K1 S1, okay, minus K1 S1. For F2 it will be equal to minus K2 S2. Now we are using these two things and finding out the answer. Fp is nothing but F1 plus F2, right? So subtracting the values of F1 and F2 here and cancelling out the K terms, what we get is sorry, not cancelling out the K terms, cancelling out the X terms. If you cancel out the X terms, you will get a K is equal to K1 plus K2. That's the final answer. Now if you observe carefully, the displacement here and the displacement here and the total displacement will be X only, because they are in parallel. Everything will go down in a synchronous manner, right? Homogeneously, like it will not go a bit more down here and it will not go a little down here. It will not go like that. Whatever you mass you apply here, the whole rod will go uniformly down, right? So the total displacement x is same for S2 as well as for S1. So this is the answer which you get. K is equal to K1 plus K2. That's the derivation for the parallel combination. Okay. So moving on to the next one, equation of a motion for free oscillation. If m is the mass of the body, it's x and it's having the force constant k, and x is the displacement at the instant t. This is the equation for the motion for free oscillation. So d square x by dt square plus k by m x is equal to 0. So when you shift it here, write k by m as w square. So it will be the actual equation. Okay. So that's the equation. Just the equation is there, no derivation. Okay. What is the natural frequency? This is the last topic in under the free oscillations. Natural frequency of damped oscillations. It is the characteristic with which a body oscillates under the action of restoring force after it gets displaced from its equilibrium position and left force. So when it gets displaced from its equilibrium position, at that time it oscillates with what frequency? That is known as natural frequency. Okay. So this was about the first topic, which is the free oscillations. Moving on, we have the second topic, damped oscillation. Let's see what are the topics in it. So this is the topic, theory of damped oscillation. There is a derivation here, and the cases are three: over damping, critical and under damping. So we'll be looking at that, and there is a small theory concept which is quality factor. So this is under the second topic, damped oscillations. So let's quickly go through it and understand what is in it. Okay. Coming to the first topic of the damped oscillations, theory of damped oscillations. Okay, what does damped oscillation means? Damped means continuously decreasing. Okay, what does damped mean? Damped means continuously decreasing. So if there is a graph here, it will be continuously decreasing and it will come to 0. Okay, that is known as damped oscillation. Now what we are trying to prove here is that the equation for it. Okay, equation for damped oscillation. So consider a body of mass m. So this is the body of mass m of a damped oscillation in a resistive medium. The resistive force is proportional to the velocity of the body and acting in opposite direction. Suppose that you put a ball here inside honey, okay, and you pull the ball here and left it. So what ball will do? Ball will slowly go like this, and it will come here again. Slowly it will come here, and means after some time it will get stopped here. So what is the resistive force acting on the ball due to honey? That is known as the the resistive medium. Okay, because of resistive medium, it's affecting the velocity. Velocity is decreasing, and finally it will come to a halt position. That is known as damped oscillation. Okay, so there is a resistive force which is represented as minus r dx by dt, where r is the damping constant, dx by dt is the velocity, and restoring force is acting on the body set for oscillations given by restoring force. So the restoring force is also minus k by x because of the Hooke's law, right? So it is minus kx as well as minus r dx by dt. So we can equate both of them, and the resultant force will be resistive force plus restoring force. Resistive force resists the total force, and restoring force is trying to bring back to the Hall position. Okay, means there are two forces acting. If you pull the ball in the honey in this direction, at that time there are two forces. One is the resistive force, which is acting in this way, the honey's resistive force, as well as the restoring force of the ball, which is coming in this direction. So the formulas of each of these we will substitute. This is minus kx and this is minus r dx by dt. So we'll substitute this, and that is the resultant force. Okay, so the resultant force will be minus r dx by dt minus kx. And then what we are doing, from the Newton's second law of motion, the resultant force experienced is ma, so it will be m d square x by dt square. Now this is the total resultant force according to Newton's law, right? So it will be substituted here. Okay, so the final equation which you will be getting is this much. Okay, till here you have to derive by using your theoretical knowledge. Okay, three formulas you need to derive: Newton's law of motion, and this is the resistive force, and this is the restoring force. Okay, after that you will be shifting the values here and there, and you will get this equation which is equal to 0 here. Then after that you will be substituting two things here. Minus r by m is written as plus 2b, and minus k by m is written as omega square. Okay, so 2b will be equal to r by m, and w is equal to root k by m. So this is the equation you have to derive for the damped oscillations. Okay, and after that you have to write the solution also. So the solution is given by x is equal to c. This you have to by heart. Okay, I'll tell you how to by heart. So you have to write first c, then d. Two things you have to write. Why two things? Because when you take the root value, it will be either minus or plus, right? Two possibilities are there. So when you take the root, there are two possibilities: either plus will come here or minus will come here. Okay, first what you write, d, c and d you write. After that you write e. Okay, after I have written that, the top thing consists of two things here. One is t, and another one is this formula. So it will be t here, and the other formula. In the other formula, what is there? Minus b plus or minus, means here it will be plus, here it will be minus, b square minus omega square. Okay, that's all what you have to write here in the means as the solution of the equation phi. So where c and d are constants, and the value of c is x naught by 2. X naught is the initial position where when t is equal to 0. X naught by 2 into 1 plus or 1 minus b by b square root of b square minus omega square. Okay, this is the values of c and d which you have to write. Now you'll be finding out the general solution. So general solution is just the substitution part here. C and d what you got here, that you will be substituting in this equation. Okay, when you substitute the values of c and d, the thing which you get here is the final formula. Okay, that's all is the general solution of the damped oscillation. Then there are three cases, as I told you. There are three cases: over damping, critical damping, and under damping. In over damping, what happens is b square is greater than omega square. You saw here the term, right? B square minus omega square. In this term, if b square is greater, that's the first case. If b square is lesser, that's the second case. And if b square is equal, that's the third case. So three cases we are considering. The first one is the over damping, which is b square is greater than omega square. So here what will happen? If b square is greater than omega square, b square minus omega square will be positive. And if this is positive, okay, if this term is positive, what will happen? If you see the equation here, if this term is positive, there is a negative term here. So this is a smaller term because we are taking root, and this is a bigger term. So a bigger minus term and a smaller positive term will return in minus only, right? So minus into t is nothing but minus t only. So e raised to something minus. E raised to something minus is the damping, means it denotes it's a damping means thing which is happening. Okay, means e raised to minus 1. What does e raised to minus 1 mean? 1 by e raised to, okay, if it is minus 6, 1 by e raised to 6. E raised to 6 is a great value, right? So if you do 1 by e raised to 6, it will be a very small value like 0, 0, 0 and all. And if it keeps on increasing, like 7, 8, 9, 10 and all, it will be more smaller values. So the values are getting decreased. That is known as damping oscillation. So if this term is negative, it will be decreasing. If this term is positive, it will be increasing. Okay, so here we got the negative term when b square was greater than omega square. So at that time it denotes it's a damping oscillation because the value will be continuously exponentially decreasing. Okay, that's what I have to write in the first case. Okay, so that's what is mentioned here. The coefficient of t is negative. This indicates that exponential decay of the displacement with respect to time. Okay, if b square is equal to omega square, at that time this will be a very small quantity, and this is the equation which you will get after taking common as e power minus bt. It will be c plus d and c minus d into delta t. Okay, so this is the graph which you have to make. For over damping it is a bit higher, displacement is higher. For critical damping it is a bit slow, lesser. Okay, And the third case is when b square is less than omega square, which is known as under damping. At that time what will happen, this term will become negative. So it is negative root of minus 1, which is I. So you are taking I here and writing omega square minus b square. Okay, so if you take omega square minus b square as n, at that time the equation will reduce to this one. Okay, that's all what you have to write for 3 cases. If they ask for any single case, write for any single case. Okay, so that's all in the topic of the theory of damped oscillation, a very important topic from exam point of view. Okay, moving on to the theoretical topic, which is the quality factor. This is the last topic under the main topic, which is damped oscillations. So quality factor means what? It is the described as the number of cycles required for the energy to fall off by a factor of e power 2 pi. Okay, so quality factor is nothing but the energy means the number of cycles required for energy to fall off by a factor. Okay, so cycles means what? Like this pendulum is going like this, right? 1 cycle, 2 cycle, 3 cycle, 4 cycle. How many cycles are required to for the energy to fall off by a factor of this much? So suppose that it is 9. So how many cycles, after how many cycles the energy will become, if it is 20, how many cycles it will become 11, after how many cycles it will become 2. That number of cycles is known as quality factor. Okay, so the formula is omega by 2b. Okay, 2b is equal to r by m, where r is the damping factor, m is the mass. Okay, so that's only the quality factor. If they ask you in the exam, you have to just write this one, explain it using an example, and the formula is this one. Okay, we are done with the second topic. The third topic is the forced oscillations. Here what we have is the derivation for forced oscillation, and here also 3 cases are there which we will be discussing now. Okay, and these are 2 theoretical topics which has the formula as well. So let's discuss what is in the derivation part. So in the forced oscillation, what does forced oscillation mean? Forced oscillation means if there is a pendulum here, you are providing an external force to make the ball move like this. That is known as forced oscillations. If you leave it freely, it will move freely. That is the normal oscillation. Forced oscillation means you are providing some force externally to make your own moves. Okay, that is the forced oscillation. So here what's happening is the external force is taken as F sin pt. Okay, everything is same. M is the mass of the body. There is a damping medium under the application of external periodic force F sin pt. That is the external force which you are putting. Okay, so what is P and what is T, we will be discussing now. So if x is the displacement at time t, the restoring force will be minus kx. Okay, and the resistive force will be minus r dx by dt as discussed earlier. So that 2 things will be same, but the only extra thing is the applied force, which is F sin pt. Okay, so the resultant force will be equal to the addition of these 3 things. Initially it was these 2 things. Now since external force is there, it will be F plus F sin pt. Okay, where P is the frequency of the external force. Frequency of external force means how frequently you are applying the force. Okay, and T is the time. Okay, so from Newton's law, the second motion ma resultant force is ma, which is md square x by dt square. And equating the equations 4 and 5, what we get is md square x by dt square is equal to these 3 sum. Okay, which we found out, resistive force, restoring force, and the external force. Okay, after that just rearranging these terms, like I am bringing down, you will get this equation is the this is the equation for the forced oscillations. Okay, now we have 3 cases. In the 3 cases, the first case is but before that we will take the value of x also. Okay, so we will be substituting this one r by m as 2b as done earlier also, k by m as omega square, and after that we are writing x, the value of x as x is equal to a sin pt minus alpha. Okay, this is the constant value pt minus alpha. This is x. If x is this, what is dx by dt? Differentiate this one to get this one. What is d square x by dt square? Differentiate this one to get this one. So that's the values of x, dx by dt, and d square x by dt square. Now we have 3 values here which will be substituting here. Okay, so when we substitute those values here, we will get this equation, and that is equal to this one. Okay, this is the RHS part and this is the LHS part. What RHS, what LHS? This is the LHS part, this is the RHS part. Okay, so just that sin pt is there, right? So what we did is sin pt, instead of sin pt, what we wrote is sin pt minus alpha plus alpha. Okay, this one is taken as a single term and alpha is taken as a single term. Now expand this, how to expand sin alpha, sin A plus B. Okay, sin A plus B is sin A cos B plus cos A sin B. So instead of A it is Pt minus alpha, and instead of B it is alpha. So we are getting this equation, sin Pt cos alpha plus cos Pt minus alpha sin alpha. Okay, now we have got this one. Now equate the coefficients of cos Pt minus alpha and sin Pt minus alpha. So here what we have is this one. So the coefficient is what? Sin alpha into f by m. So we'll see where all the cos Pt minus alpha terms are there. Here it is there. Yeah, that's the only term. So here what's the coefficient? 2 bpa. So 2 bpa will be equal to f by m into sin alpha. Like that we'll do for the sin term as well. So we'll get 2 bpa by 2 bpa is equal to f by m sin alpha. Same thing if you do for the sin Pt minus alpha, we'll get this term here as the equation. Now what we will do is squaring and adding. We'll square these both terms, okay, and then add these both terms. So what we get is f by m square in the RHS part, as well as sin square alpha plus cos square alpha, which is 1. So squaring this term here, we'll get this term here, and then we'll be just finding out what is alpha square. Shift this term in the denominator of this one, so we'll get this one. Take the root, you'll get a is equal to f by m root of 4b square p square minus omega square minus p square whole square. Okay. So what equation you got is the amplitude for the forced oscillations. Okay, before what you had got, that was for the displacement. Okay, this was for the displacement equation. Okay, what I mean is this one. This equation is for the displacement. Okay, motion of the forced oscillations, and if they ask for the amplitude, you have to derive till here. Anyway, if they ask you for the forced oscillation, do both of the things. Okay, that's the total marks for. Okay, so you can also find the alpha value, which is the phase, by dividing the equation 8 and 9. What are the equations 8 and 9? Equations 8 and 9 are this one. If you divide it, what you will get? Sin alpha by cos alpha, you will get tan alpha. So alpha value is tan inverse of whatever you get in the RHS part. So what I was talking about is this one, alpha is equal to tan inverse of this one. Okay, this is the equation for phase of forced oscillations. So under the topic forced oscillations, derive three things. First is motion, second is the what we derived just now, and third is the phase of the forced oscillation. Okay, so these three things you have to derive for the given question forced oscillation. Second is the amplitude. Okay, these three things you have to derive. Okay, after that they will ask you for a particular case, like derive for the particular case p is less than w, p is equal to w, and p is greater than w. So for these three things, just the formula will differ by a small variation. So let's see what is the small variation. So p is nothing but the angular frequency of the applied force, and w is the natural frequency. Okay, if p is less than w, p square is a very small value. Omega minus p square will be approximately equal to omega. 2 bp will be equal to 0. Why? Because p is very small. So what amplitude we get is a is equal to f by m omega, m omega square. Why omega square? What is the value of a? Substituting the value of these things here, like p is very small, so we can ignore this one. P is very small, you can ignore this one, and then take the square root. You will get a is equal to f by m by omega square. Okay, and phase also you will get as 0 because p is 0, so a bottom will be 0, and that is the 0. So in case when p is very less than w, at that time what's happening is displacement and the force will be in the same phase, because angle is 0. Both will be in the same phase in the graph. Okay, like this, the waves will be same. The second case is p is equal to w. If p is equal to w, omega square minus p square is 0. Substitute this value in the equation of a, you will get this one. Substitute the value of this one, p is equal to w, in the equation of alpha, you will get tan inverse of infinity, which is pi by 2. So the phase will be of difference of pi by 2. Okay, means if the one starts from 0, other starts with pi by 2. Okay, there will be a phase difference of pi by 2. The third case is p is greater than w, which is the damping forces are very small. It is significant only when damping forces are small, which means if p is greater than w, this will be approximately equal to p power 4, because if square is there here, that will be p power 4 here. So substituting that value here, what we get is a's answer as this one. Okay, and amplitude's answer, if we simplify, I'll get as this one, f by m by p square. Okay, this is very important from exam point of view. Whichever case they ask, derive for that one under the topic forced oscillations. Okay, same thing goes for phase also. Just substitute the value what you got in the equation of the third case in the tan inverse of formula. So what answer you get is pi. So if p is greater than w, the displacement will be phi. Displacement will be pi. Okay, this was about the forced oscillation. These are the important derivations. Make sure you go through it very well and practice before going to exam. Okay, so coming to the theoretical topic, which is resonance and condition for resonance. So in resonance, what will happen? A will be maximum value, amplitude will be maximum. And when will A be maximum? If I ask you simply when will A be maximum, A will be maximum when this value is maximum and this value is minimum. If this is minimum, at that time B should be minimum. If B is minimum, at that time P will be equal to W. That will also contribute to the minimumness of the root value. So if these two are equal, this will get cut, value will be minimum, and if B is minimum, this whole value will be minimum. Okay, so the A value of max will be F by M by 2 BP, which is nothing but 2B omega. Okay, because P is nothing but the frequency of the external applied force. Since P is equal to W, we are writing here directly W. Okay, that is the equation for the resonance in case of like maximum resonance. Okay, and sharpness of resonance, what is that? The rate at which the amplitude changes with respect to frequency of applied force, that is known as sharpness of resonance. Okay, so I've discussed the oscillations topic. Let's move on to the last topic, which is the shock waves. Okay, so what is the main thing which you have to keep in mind is here numericals also will be there. Okay, so we'll be solving numericals in another video, but in this video it's just the theoretical topics. So the formulas is the main thing you have to remember is Mach number. Okay, and what are the properties of shock wave? Very important: construction, working, and working of Reddy shock tube, and the application of shock wave. These all things are repeated questions in exam. Okay, so make sure you learn this thoroughly. Okay, so let's get started with the shock waves. What is there in that topic? So shock waves is nothing but a wave moving faster than the speed of sound. So before that, understand what is Mach number. Mach number is nothing but the ratio of the speed of the object to the speed of the sound. If there is an object A which is moving like 1000 ms per second, okay, and what is speed of sound? 333 meter per second. Okay, so if this is moving faster than the speed of sound, that is known as the shock wave. Okay, so that is known as the Mach number, the ratio which is getting calculated, object speed by speed of sound, that is the Mach number. So if Mach number is higher than 1, what does that mean? The object speed is more. If it is less than 1, what does that mean? Object speed is less. Okay, so object speed is written as V and speed of sound will be written as A. Okay, now there are few types of waves. The first one is the acoustic, ultrasonic, subsonic, and supersonic. Acoustic is the normal wave, 333 meter per second as the sound. Ultrasonic is which produce the frequencies beyond 20,000 hertz. Subsonic is the wave which is less than the speed of sound, and supersonic is the wave which is more than the speed of sound. Shock waves is a thin transitive surface of a fluid medium propagating with a supersonic speed, characterized by the instantaneous change in pressure, temperature, and density. So shock wave is a special case in the under the topic supersonic waves. So it's also a supersonic wave, but there will be a change in pressure, temperature, as well as the density of the medium. Okay, that is known as shock waves. So one of the example is shock wave is produced when the earthquake happens. Okay, so that's all what you have to write. If they ask you about the shock wave, explain what happens in the shock waves and give them an example, and after that you have to write the properties as well. Okay, very important properties of the shock wave. It's travel in a medium with Mach number exceeds 1, and shock waves are produced by sudden dissipation of energy in a medium, and it obeys the laws of fluid dynamics, and change in entropy of the medium due to the generation of shock waves. So there is a change in the entropy, which is the energy present in the medium, and shock waves are confined in a medium of very thin space. They are not electromagnetic in nature, they are not physical waves. Okay, these are the properties which you have to write in the exam. Okay, then coming to the important topic of the shock wave, which is the construction and working of Reddy shock tube. So what is Reddy shock tube? In Reddy shock tube, it's like a small gun which can held in your hand, and by using this you can produce the shock waves. Okay, so firstly what you have to write is the construction part. Make the diagram, write the construction of means the construction part, what is the each of these things mentioned here, and after that you have to explain how it works. So let's go through each one by one. Firstly, make this diagram here, make a rectangle like this, and there is a piston here. Okay, after that it's divided into two parts here. Okay, two parts it's divided into, and the outer surface is made of the steel. Okay, it's a cylinder. Okay, it's a cylinder like this, and it's made of steel, and it is of 1 meter total. Okay, 1 meter total, and the diameter of the steel is 30 millimeter. Okay, so it's a very thin small tube. Okay, and there is a piston attached here. Okay, for pushing it. Now what we will be pushing? We will be pushing two gases. Okay, there will be gas 1 here, there will be gas 2 here, and this is nothing but a thin aluminum foil. Aluminum foil is in between the half part here and half part here. Okay, and these are the sensors, and this is the pressure gauge. So how many things are there? First, this is the cylindrical tube. It is having a piston here. It is of 1 meter. the diameter is 30 millimeter. It is divided into two parts by a thin diaphragm which is made of aluminum, and this is the gas 1 part, gas 2 part. Okay, this is the driver's gas, this is the driven gas, and after that we will be pushing the piston here. So what happens when you push the piston here is that this will get burst. When this will get burst, at that time what will happen, the waves will form, right? Waves will form and it will get reflected back, and again it will come from here. So like that it keeps on happening until it produces the shock wave. When it produces a shock wave, what will happen, a cooling wave will come from here and normalize all of the shock waves present. Okay, so that's the working of it and the construction part. So the main things you have to mention, it consists of a cylindrical stainless steel tube of 30 millimeter diameter and 1 meter in length. Okay, it's divided into two sections, driver and the driven section, and separated by a aluminum of thickness of 1 millimeter, 0.1 millimeter. Okay, and one end of the piston is filled with driver's tube, which is having the driver's gas, and second end is the driven gas. Okay, and there is a digital pressure gauge in the driver section, which is the pressure gauge. This is the pressure gauge. Okay, and these are the two pressure sensors. Okay, so these are the two piezoelectric sensors to measure the pressure and all, and one of the end is closed, other end can be closed or it can be open, and it has two test gases, the first gas and the second gas. Second gas is known as the test gas. So what is the working, as I explained, the same thing, push the piston, break the diaphragm, and it will produce the waves. It will change the temperature, pressure and density. All will happen in 1 millimeter, 1 millisecond. Okay, one or a few millisecond time it will happen, and finally the expansion wave will come and it will neutralize the compression, and after that it will get over. Okay, at that time what happens is the piezoelectric things will be measuring the changes which is happening, okay, in the pressure and all, and that will be recorded. Okay, that is known as the so this is the working of Reddy shock tube. Okay, and the characteristics are the following. It operates on the principle of free piston driver shock tube. It is a hand operated device. It can produce the temperature up to 900 Kelvin. It is capable of producing Mach number 1.5. Okay, and the applications are as follows: cell information, like using the shock wave to get the DNA information; wood preservation, inserting the what are the gases required inside the wooden materials; and pencil industry to get the pencil used to the wood which is being attached on it; kidney stone treatment; gas dynamic studies; shock waves assisted drug delivery, means without the needle, we'll be using shock waves to deliver whatever is required in the patient; and treatment of dry bore well. Okay, so that's all what is there mainly in this module. So thank you so much for watching. I'll see you in the next one.